let us see how these behaviors are. As I said, when I look at the stress strain curve, you get the peak value and the residual strength. So at large strains, the soil possesses some strength which is much less than the peak value. So if you are able to control the strains in the ground, you may use peak value like we do it in foundations. In case of slopes where the large displacements are possible, we go for residual strength. So we need to determine both peak and the residual strength. And if you look at the peak strength, I'll get cohesion with respect to peak strength and the angle of shearing resistance with respect to peak value. If I look at the residual one, usually residual condition C is 0, very close to 0, and the angle of shearing resistance is phi r. So based on these two, we can plot the mode circle and determine strength envelope with respect to peak strength and with respect to residual strength. This is typically true, and for overconsolidated soils, maybe this phi r may be slightly more than the phi due to peak strength. And if you allow long time, like in the laboratory, we do the test in within an hour or two. But in nature, the shear stress is mobilized over a long period of time, maybe 1 year, 10 years, 100 years. What you find is the strength decreases with rate of loading. So what you get in the laboratory is relatively high strength, and in the field I may have to apply a smaller value, and the reduction is usually about 3 to 20% per log cycle. Suppose I shear it in 1 minute. If I shear it at 10 minutes, the strength reduces by 10%. If I take 100 minutes, strength may reduce by 20%. 1000 minutes, 30%. So when you translate your lab data to the field, you may have to figure out how fast or how slow is the shear stress being applied in the ground. This is stress strain properties we looked at: dense sand, loose sand, and here is volume contraction and dilation. Please note that the failure in case of dense sand is around 4% strain. In case of loose sands, it continues to mobilize strength, which is low, of course, even up to about 20%. And at 20% strain, residual strength of dense sand is equal to the strength of loose sand. And at high confining pressure, even dense sand does not dilate, and you will find that the peak is much lower now. And here, if I look at dense sand with high confining pressure, you will find it may compress. So dilation is possible only when sigma 3 is small. Under low confining pressures, the chances of volume increase is there. So here is the situation. I have a loose sand, which means a high void ratio, and I have a dense sand with lower void ratio. As the confining pressure increases, then you will find that the critical void ratio line keeps changing. Under low confining pressures, this can dilate and loose sand will contract. As you increase the confining pressure, the dilation will be much less and the contraction will be more. So, as I said, dilation is significant only when you have dense sands and low confining pressures. And this is the critical void ratio. No matter what is the initial state of void ratio, loose or dense, at large strains you have a unique void ratio, which is called the critical void ratio. This is dense sand. Of course, we have two ways of plotting. We also sometimes plot ratio of sigma 1 by sigma 3, and you will then get a much good stress strain curve, and I can pick up the peak value better. When you have the ratio, this is a better way of plotting, and the same data we plotted earlier in terms of the ratio you can see here. This is the loose one, and as you can say, this is our, and when I plot this in undrained condition, the pore pressure is positive. So what's happening? Loose sand, normally consolidated clay, you have one strength, and if you have dense sand over-consolidated, you have a higher strength. Then we also try to look at it. Most of the tests are triaxial, but in the field you have a long embankment, which means it's a plane strain problem, and the difference between these two in terms of friction angle or angle of shear resistance is about 4 degrees. Please remember, if I determine from triaxial tests a certain angle of shearing resistance, in the field I may have to use something slightly larger. So the angle could be about 3 degrees more. And in case of over-consolidated soil, initially the strength is more, and normally consolidated soil you have a linear behavior, whereas in the over-consolidated soil, up to pre-consolidation pressure, soil exhibits an additional resistance. Over-consolidated clay is stronger and stiffer. This is normally consolidated clay, over-consolidated clay. You can see the stress strain curve is steeper, so E value, modulus of deformation, is high, strength is more, but at large strains, both are approaching each other. And if I look at the volume change for clays too, a normally consolidated clay contracts and an over-consolidated clay dilates. Same thing what we plotted earlier. And if I have a consolidated undrained test, because of the increase in pore pressure, sigma 3 decreases and p value decreases. So even though the D matrix is increasing, the Q value decreases and the stress path comes back. This is the total stress and this is the effective stress path. The difference between them is the pore pressure. And the pore pressure increases at failure, it's the largest value. In case of over-consolidated clays, the pore pressure is negative, so the effective stress path moves to the right and not to the left. So this is the total stress path and this is the effective stress path, and that means because of the negative pore pressure, effective stress are high and you get a very high strength for over-consolidated soils.